This video covers the second half of section 4-4 and 4-5, which is on the multiplication rule, and I'm going to be on pages 38 and 39 of the note-taking guide. Last time we looked at the case where our two events were independent, meaning they did not affect each other, and we said to find the probability that they both happen, well, we would take the probability of the first event and multiply it by the probability of the second event. Well, now we're looking at the case, well, what if they are dependent? Meaning my first event might affect my second event. Well, here we're going to take the probability of the first event and we're going to multiply it by the probability of the second event. However, we have to assume that the first event occurred. So this notation here, this is the probability of B assuming A occurred. So, and this little symbol here, which is new, is read given that. So we would read this, the probability of B given that A occurred. So now let's come back to this case where our two events were independent. So if A and B do not affect each other, well, the probability of B given A, well, these don't affect each other, so it doesn't matter whether A occurred or not here. So this would be irrelevant because they are independent. So this is just the same as saying the probability of B. So you can see if we're independent, we come back to the case where we're just the probability of A times the probability of B. So let's look at an example here. So from an urn containing 3 blue balls and 2 red balls, you select 2 balls without replacement. What is the probability that you have 2 blue balls? Well, here this would be dependent because let's say I select a blue ball on my first occurrence. Well, now when I go for my second ball, there are fewer blue balls left in the urn, so therefore that first selection affected the probability of the second. What we want to do here is draw this tree diagram again. So we could have blue or red on our first draw, and then on my second I could also have blue or red. So on this first selection there are 3 blue balls out of 5, so this would be 3/5. And there are 2 red balls out of 5. So now I'm going to come down here to my second. So I'm assuming that I got a blue ball in the first, so I'm going to mark one of these off. So now to get a second blue ball, there are only 2 blues left out of 4 now, and 2 reds out of 4. If I want the probability of getting 2 blues, well, that happens when I get a blue and then another blue, so that happens here. So this is going to be the probability of a blue on my first and a blue on my second. So I hope you understand this little notation. Since both blue and blue start with a B, I'm going to use a little subscript there. That's going to be the probability that I get a blue on my first times the probability that I get a blue on my second, but I have to assume that I've already gotten that blue on the first. So this is going to be 3/5 times 2/4, which would be 3/10. So next we ask, what is the probability that both balls are the same color? Well, that could happen here if I get a blue and a blue, or it could also happen over here if I got a red and a red. So now I need to assume that my first selection was a red. So this guy is back in the pot, but now I got a red. So the probability that I get a second red, well, now there's 1 left out of 4. However, there are 3 blues left out of 4. So this could happen 2 places, where I get a blue and a blue, where we just found, or when I get a red and a red. So let's see if we can find the probability of a red and a red. So that's going to be the probability that I get a red on my first times the probability that I get a red on my second, assuming that I got a red on my first. So this is going to be 2/5 times 1/4, which is going to be 1/10. So here, to get 2 blues would be 3/10, and then to get 2 reds would be 1/10. So the probability that they are the same color is going to be 3/10 plus this other probability, which would be 4/10 or 2/5. Now I'm aware that we haven't gone into great detail about why I added these 2 probabilities here. We're going to come back to this in the next section. But what's important that you understand today is why these probabilities change, because we did not replace, and this tree diagram is also helpful here for dependent events. So in the game of 5-card stud, what is the probability of a flush? So a flush is when you get all of the same suit. So in case you don't remember, there are 4 suits, each with 13 denominations in a standard deck of cards. So let's see if I can draw this out here. So we have 52 cards with 4 suits, each having 13 denominations. So we want to know what's the probability that if I pull 5 cards without replacement, all 5 cards are the same suit. The probability of a flush. So we're going to first say, well, what's the probability of that first card? If I'm in search of a flush, my first card could be anything. Really, because I haven't specified what suit yet. So my first card could be anything. Then my second one, so once I pull that first card, now I need to get the same suit given the first. Well, then my third card, well, that one still needs to be the same suit given the first card and the second card, and so off, and so forth. So let's see here. The first card could be anything. So I could pick any card here. Let's say I pick the 7 of clubs right here. So the probability that I get any card in the deck, well, there are 52 out of 52, or 1. So anything would work for that first one. So now that I have selected a card here, I got the 7 of clubs, now I know that the rest of my cards have to also be clubs. So what's the probability that I get another club? Well, now there are 12 clubs left out of a total of 51 cards, because I've selected one. So let's say, all right, I got this one now. To get another club, well, now there are 11 clubs left out of 50. And let's say I get this one. Now there are 10 out of 49. And then lastly, 9 out of 48. So if we were to multiply this out, we would get 33 over 16,660. So just in case it's been a while since you've worked with fractions, or if you just don't want to get bogged down in the computational details, I want to quickly show you how we would do this in the calculator. So if you're not on your main menu, you can select menu, and To do arithmetic, we go to the Run Matrix menu, which is number 1. Now I have some stuff in here from before. If you wanted to get rid of that, you could choose delete and delete all. So I want to multiply these fractions as I have here. So 1 times, well, that's not terribly difficult. Now next I want to enter 12 over 51. If you see above the 7 right here, we have our fraction button, which fills in the fraction, and then I can just type in 12, and I'm going to use my arrows to move down here for 51. And then I'm going to move over here, times, and then again I choose my fraction button, 11 over 50, and so forth. And then once we have all this entered, we can select execute, and my answer is given here as a fraction. If by chance your settings might be different and it does not give you this as a fraction, if you come down here above the number 8, you see a fraction to decimal button. This would change things from a decimal to a fraction. So as a decimal, you see this is listed in scientific notation, which would tell me to move my decimal place 3 places to the left. 1, 2, 3. So this would be 0.00198. So this would be a very small probability. So next I want to come back to that idea of the complement that we talked about last time. So it's sometimes easier to find the probability of a complement as opposed to the actual event. So one case where we see this often is when I say, well, what's the probability that at least one of some event happens? Well, you wouldn't want to have to find the probability that 1 occurs, 2, 3, 4, and so on. It would be easier to do 1 minus the complement. So the complement that I get, let's say here, let's look at an example, that I get at least 1 blue ball. Well, in this case down here, I would have to find 1, 2, or 3. So the complement, or the opposite of getting at least 1, would be that I get none. So let's come down here and look at an example. Here we have an urn containing 3 blue balls and 5 red balls. You select 2 balls without replacement. What is the probability that you get at least 1 blue ball? So let's draw our picture here. So on my first ball, there are 3 blues out of a total of 8 balls. So this would be 3 eighths that my first is blue. And there are 1, 2, 3, 4, 5 reds out of 8. Now for my second ball, here I'm in the case where I assume the first was blue. So I've already selected one of these blues, so I'm going to strike this one out. So now there are 2 blues left out of 7. Or there are 5 reds left out of 7. Now let's look at the case, well, let's assume I got a red. So I'm going to put this blue ball back in the bucket. And I'm going to say, well, let's assume I got a red. So the probability that I get blue now, well, this one's back in, so there are 3 out of 7 blues, or there are 1, 2, 3, 4 out of 7 reds. All right, so the question we asked was, what is the probability that I get at least 1 blue ball? So here, if I got a blue and a blue, well, that would be 2 blues. If I got a blue and a red, that would be 1 blue. If I got a red and a blue, that would be 1 blue. And if I got a red and a red, I would get no blue. Well, this is why our little shortcut here, 1 minus none, helps us. Because to answer the question as is, I would need to find this probability, this one, and this one, which is feasible, but it's a good bit of work. So it would be easier, the probability of at least one blue would be 1 minus the probability of no blues. Well, in the case where I'm finding no blues, there's only one place where that happens, right here. So that would only require me to find one probability as opposed to 3. So this is going to be 1 minus the probability that I get a red on my first times the probability that I get a red on my second, given I got a red on my first. So this is going to be 1 minus 5/8 times 4/7, which equals 1 minus which would be 9/14. So in some cases, specifically cases where we see at least one, it's oftentimes easier to find the probability of none and subtract that from 100%. So let's look at an example here. Suppose you have 5 children. What is the probability that you have at least one son? So I could draw this tree diagram out here, which is going to become quite cumbersome. So here you see that there are quite a number of options. So the probability that I have at least one son, well, that would be, here my first son's a boy, so that would be all of these over here. So basically it would be everything except this last case over here where I have all girls. Well, I don't want to find all of these options. So my shortcut, the probability of at least one boy is going to be 1 minus the probability of no boys. So if I find the probability of no boys, well, that's only one case. So that's going to be quite much easier. So this is going to be 1 minus the probability of a girl times the probability of a girl Now I immediately knew that these bursts were independent because we've already talked about this. But let's say that didn't jump out at you. If you said, well, what's the probability that I have a girl on my second given that I had a girl on my first? Well, those aren't going to affect each other, so it's just going to be the same. Each child, the probability of a girl is going to be a half. So this would be a half times a half. So this would be 2, 4, 8, 16, 32. So this would be 31 out of 32 chance that I have at least one boy. So next we have 5 students are selected at random. What is the probability that any of these students share the same astrological sign? So I'll give you a little hint here. There are 12 astrological signs. Again, there are a number of cases. We could have one pair that share, 2 pair that share, or 2 different pairs of 2, or maybe all 5 have the same astrological sign. There's quite a number of possibilities here. So the easiest way to find this is going to be 1 minus the probability that we have no shared signs. And hopefully you can see that this would be shorter than finding 1 pair, 2, 3, 4, 5, and so forth. So this is going to be 1 minus, well, what is the probability that my first person gets an original astrological sign? Well, this first person gets to not choose, but could be any of these. So let's say this first person was a Cancer. Well, they had 12 out of 12 options. So now my second person, well, one Cancer has already been claimed, so the probability that they do not share an astrological sign would be 11 out of 12. So let's say they chose this one, and so forth. So this would result in a probability of 89 over 144. So again, if that arithmetic is bogging you down, we could come to our calculator and do 1 minus, select our fraction button, which would result in a probability of 89 over 144. And once again, if your result was not given to you as a fraction and you preferred a fraction, you could select the fraction to decimal button. So this is about 62%.